Yeah, okay. Good day to everybody. It is a pleasure for me to speak on this conference. My talk is related to functors related to selection principles and cardinal invariants and some topological properties. So the next file is, can you move the file? Okay. Functors are related to categories. Categories have objects, ob of C, and homomorphisms. For example, category of topological spaces, objects are topological spaces, and the morphisms are continuous mappings between these. So if we have two categories, then a mapping F capital from C1 to C2 is called the covariant functor if the following conditions are satisfied. To each object from the first category, f of x is the object in the second category. And for mapping, morphism from the first is assigned to the morphism in the second category. Stop, please. So some conditions for the functor must be satisfied for the previous slide. And some examples important for topology are, for example, well-known exponential functor f of x and variants of this x span of x with the vectorist topology, hyperspace with the vectorist topology, then the functor of superextension, the functor of complete link systems, the functor of probability measures, for example. Next, please. Next slide, please. Can you move? Okay, so we are going now to consider the following things. We have two properties, topological properties, P and Q, and we are interested if X has P, for example, does the f of X has the other property Q, especially X has P even if f of X has P. And my talk will be related to this, the second notion. And if we call two spaces F equivalent, F is factor, it is the case f of X and f of X are homeomorphic as topological spaces, and which properties are preserved by F equivalence. It is a natural question in this field. And we suppose that all spaces considered in this talk are Hausdorff. So now I am going to present some results about, please, next. Next slide, please. The first functor that we consider here is the functor of G permutation degree. We have Sn denotes the permutation group of the set of first n natural numbers. G is subgroup of this group, and the x to the n is the nth power of the topological space X. And now we are we now consider how the permutation group G x to the n, 2 points in the space x to the n are called G equivalent if one of them, for example y, is obtained as a result of permutation, of application of permutation, some permutation sigma in G to the first point x. Next slide, please. And we have the space SP NG of X and the mapping P NG and X to the N to the this space SP GN of X, defined in this way. The equivalence class X1 of the element X1, X2, Xn is mapped to the equivalence class of X1, X2, Xn, equivalence class. So element of X1 from X to the N is mapped to the equivalence class of this element. Okay, next. And this space equipped with the quotient topology is called the space of NG permutation degree of, if it is clear that N is fixed number, we speak about the space of G permutation degree of the space X. And when G is equal to the whole permutation group S to the N, we remove the prefix G. So we have also the mapping SPGN related to the mapping between two topological spaces X and Y. So this mapping SPGN sent F to in the following way. Equivalent class in the first space is assigned to the equivalent class of the images of coordinates of the first point in the space X. In this way, we get a so-called normal functor SPGN in the category of compact spaces. It is normal in this category, and their continuous mappings. This functor is called the functor of G permutation degree. And we shall see now which properties are preserved. So this functor is similar to the functor Xn of X with the Vietoris topology. So in fact, this functor XPN of X, XPN, is a subfunctor of the functor of the G permutation degree, and in the case n equal 2, these two are equivalent, homeomorphic. But there are examples showing that for n bigger or equal to 3, these spaces are not homeomorphic. Such an example can be found in the book, short book by Fedoshuk and Filipov, Topology of Hyperspaces and its Applications, published in Moscow in Russian language. Okay, and now we are going to discuss some selection properties and preservation of these selection properties under the influence of functor of the G permutation degree. So I start with one definition. Open cover of a space X is called omega cover if each finite subset of X is contained in a member of the cover. And now we have definition of some selection principle. Space X is called omega Rothberger if for every sequence UN of omega covers of X, there is a sequence of UN such that each UN is element in the corresponding cover UN, and the collection of selected elements from these covers MEN is also omega cover of X. The next notion is on the next slide is the notion of omega Menger space. It is similar for each sequence of omega covers, UN of omega covers, there is a sequence Vn such that each Vn is a finite subset of UN, and the collection union of all selected Vn's is also an omega cover of X. And so now we have the result which says that functor of G permutation degree preserves this property. So for space X, the space SPG N of X is omega Rothberger if and only if the original space X is omega Rothberger And the similar result holds for Menger property. The space SP Gn of X is omega Menger if and only if X is omega Menger. Now we are going to find to see some other properties which are preserved by this functor. So we need some notation. The symbol G denotes the collection of covers of a space X by G delta subsets. G delta subsets are countable intersections of open sets. And if elements of this cover has the property that each compact subset of X is contained in a member of the cover, then this cover is called Ulster cover, and the notation is GK. GK is the notation for the Ulster covers. Ulster is the Polish mathematician, and he defined some spaces called nowadays Ulster spaces. We are going now to see the definition of this space. Next page, please. So this notion was introduced by Ulster in a different way. But in this paper, Babin Kostova, Pansera, Skippers, they show that it can be expressed in terms of selection principles. So we have the following as a definition. The space X is Ulster space if for every sequence UN of elements of GK, we defined in the previous page, there is a sequence UN one from each such that selected elements form an cover from G. And now we have the result, interesting result, a space, okay, it is on the previous, the space CP Gn of X is Ulster if and only if the original space X is Ulster. The next we are going to see some other properties which are preserved. So a space is called weakly, strongly star Menger if for every sequence UF of open covers there is a sequence of finite subsets of X such that union of stars of Fn with respect to corresponding UN is a dense in the space X. This notion was introduced in the paper by Kumar and Tyagi, published in Kubo 2-3 years ago, and the result related to functors says that a space X to the n is weakly strongly star Menger if and only if the space of G permutation degrees of X is also such a space. And now we are going to show, next please, this notion of nearly strongly set star Menger spaces is defined in a paper by myself and my collaborators Shukran Kondra and Sumit Singh from India, published in Mathematica Slovaka, and the space is called nearly set strongly star Menger if for every A subset of X and every sequence UN of open covers of X there exists a sequence of finite subsets of X, Fn, such that A is contained in the union of stars of Fn's with respect to UN. And the result says that if the space of G permutation degrees of X is set strongly star Menger, then the space X to the n is nearly set strongly star Menger. Okay, now we are going to demonstrate some result related to cardinal functions. I will mention only one result related to cardinal functions, and it concerns the notion of so-called set tightness introduced by Arkhangelsky, Isler, and Tironi. So the set tightness at the point X of the topological space X, which is denoted by Ts of XX, is the smallest cardinal number kappa, such that whenever X belongs to the closure of some set C, but not to the set, then there is a family gamma of subset of C having cardinality less than or equal to this cardinal kappa, such that X belongs to the union of this, the closure of the union of this collection, minus union of closures of elements of this collection. And the set tightness of X is defined as the supremum of local set tightness of the points in the X. And the result says that if X is a regular space, then the set tightness of the space X to the n is equal to the set tightness of the space of G permutation degree over the space X. It was the first part of my talk, and the second part will be related to the probability measures, idempotent probability measures to be more precise, and it is a part of so-called idempotent mathematics. So idempotent mathematics is a field of mathematics in which fields of real numbers or complex numbers is replaced by some new so-called semi-fields. The typical example of this is the so-called R maximum is the union of minus infinity with the operations, new operation now given. The first operation, addition, is in fact maximum of X and Y. And the multiplication is the usual addition of these elements. So this is completely new, so-called non-linear part of probability measures and the theory of spaces of probability measures. Let's go to the next to see these three books gives the good source for people that want to study idempotent mathematics. Okay, let's go to the some new definitions and results. We are going now to consider the idempotent probability measures. This definition of such kind of probability measures was given in this paper, in this book, in fact. And the formal definition is the following: a function mu from the please go back. The function mu from the set of Borel subsets of X to the extended positive real numbers is said to be idempotent measure on X if the following conditions hold. Go, please. So mu of empty set is 0. Mu of the union of two sets is maximum of mu od A, mu od B. So you see that here linearity for the usual measure mu of union is equal to the sum of union measures of sets A and B, but here it is maximum, so linearity is destroyed. And the next measure of the union of any directed collection of subsets of A is supremum of measures of these elements of this collection. For every increasing net, that means that the set of indexes is directed set, and it is the subject of this talk. Okay, the second part of my talk. So idempotent measure mu on X is called idempotent probability measure as usual if a measure of the whole space is equal 1, and we denote the set of all idempotent probability measures on X by I of X. Okay, now we gave in this paper by myself and my collaborators from Uzbekistan, Zaitov and Eshembetov, we applied a new approach to the definition of the topology on the space of idempotent probability measures and in general in probability measures. The previous definitions used functions, and we use families of open subsets of a basic space X. So let's see now the formal definition. This. So we have a compact Hausdorff space. Probability measures are usually defined on compact Hausdorff space. Later we shall extend this to the a wider class of Tikhonov spaces, thanks to the definition on compact Hausdorff spaces. So B is a base of X, and elements, we have finitely many elements from this base, and epsilon bigger than 0, positive real number. So for me, we define the neighborhood of me by using these open sets from the base of X, defined in this way. And the base in the space I of X is defined as the union of the bases related to the concrete measure in the space. Okay, so it is absolutely new approach to the definition of topology on the space of idempotent probability measures. So this family forms a base for the topology on I of X, the space of idempotent probability measures, and this topology coincides, it is very useful, with the topology induced from the product topology R to the collection of Borel subsets of X. So if we restrict this topology to the set of idempotent probability measures, we get so defined. And now we, for the proofs of main results, we essentially use these results. For an open set U of X or closed F of X, the sets U minus and U plus defined in this way are open sets, and sets defined by using closed sets F, F plus and F minus are closed, and it will be used in next theorems. So go please. The result that for compact Hausdorff space X, the topological space of idempotent probability measures is also a compact Hausdorff space was proved by Zarichny in this paper, published in the Vestia Mathematica in 2010, but we gave completely new proof of this, of the same result, that for compact Hausdorff spaces, the space I of X is also the same, by using our definition of topology on this space. So it is one of results in this talk. For mapping F of a compact Hausdorff space X, we defined the result of action of functor I to F, which maps I of X to I of Y, defining this by this formula. IF of me of B is the measure of the pre-image of B, where B is a Borel set in the space Y. So it is the definition of this action of this functor. And now we have a so-called tau-smooth idempotent probability measures. We define now first outer idempotent measure on arbitrary set, subset of X, defined by mu star of A is infimum of mu B, where B is superset of A and belongs to the class of Borel subsets of X. So we get an extension mu star of the original measure mu. And now we shall take Tikhonov space, not compact space, but we shall take a Tikhonov space. Each Tikhonov space has a stone-Čech compactification denoted by B of x, and we now defined the space I tau of x. That means of tau smooth idempotent probability measures on the space x, defined in this way. It is the collection of all probability measures, idempotent probability measures on x, such that this condition is satisfied. Mu of f is equal to 0 for every Borel subset f of x, which is contained in the remainder of x in the stone-Čech compactification of this space. So we use here essentially the definition for the compact spaces, and now we extend to Tikhonov spaces. For each tau smooth idempotent probability measures, we defined a function mu tilde from the collection of Borel subsets of x to the real line by this formula. Mu tilde of a set A is exactly the mu star of A, which is infimum of measures of B, where B is a Borel subset of X and superset of A. And this is a tau smooth idempotent probability measure on X. So not on compact, but on Tikhonov spaces. Now several properties. First, let me define for continuous mapping F between Tikhonov spaces. We define the mapping I tau from I tau of x to I tau of y defined by this way. So it is the restriction of idempotent probability measure functor restricted to the set of tau smooth probability measures. Again, we use first definition, original definitions for compact spaces, and then restrict this to the class of Tikhonov spaces restricted on this special kind of new spaces. Several properties are given now, please. So this functor, I wrote here mapping I tau, this functor preserves the class of perfect mappings. So if some mapping f between x and y is perfect, then the I tau of f is also a perfect mapping. Then this mapping I tau preserves the class of embeddings, and this class also preserves pre-images of Borel sets. These properties of these are very, very, very nice properties. And okay, go to the next. And here is one of main results, absolutely the main result, in fact. Topological space X is called Čech complete if X is a Tikhonov space and the remainder beta X minus X in the stone-Čech compactification is F sigma set. F sigma means that it is a countable union of countable many closed subsets. And for example, all local compact spaces or non-class are Čech complete, but the converse is not true. For example, the space of irrational numbers or in the real line with the relative topology is an example of Čech complete space that is not locally compact. And now we show the theorem, non-trivial theorem, that operation I tau, the functor I tau, preserves the Čech completeness of Tikhonov spaces, Čech completeness of Tikhonov spaces. So more precisely, the space X is Čech complete if and only if the space I tau of X is Čech complete. This result was proved for non-linear case, which means for probability measures probability measures, not idempotet, and not tau smooth by Banach in this paper, Topology and Probability Measures, published in 1995. And thank you very much for your attention.
Thank you, Professor Kocinac. Is there any question on this talk?
Yes, I have a question, Mehmet Baran.
Who is?
You can come and
It's nice to hear you from.
any question from the participant?
Okay.
It's a nice talk.
Come and ask.
I am listening.
It is a nice talk.
Thank you for your presentation. I have one question about the definition of probability measures. The definition
Of idempotent probability measures, huh?
measures, yes. You can go to the slide. Why did you use the second, the probability of A union B equal to the max? We know that it,
because okay. Finish your question, please.
Yes. Okay.
So we replace the usual field of real numbers or complex numbers by a new field, and the new operations are defined. So the first operation plus in the circle is maximum. So that is the reason. For usual probability measures, we use mu of union is the sum of measures of subsets. Mu of union of A and B is the sum of mu on A and mu on B. But here we use another operation. It is maximum. So that is the reason. And also the third property, the supremum of measures of some subsets instead of sum of the subsets for the same reason. For the same reason. The change of the field is essential for the definition. Okay?
Thank you. Is there any?
Okay.
Yeah, I have a question, Mehmet Baran.
Mehmet Baran,
Thank you.
online.
It's a very nice talk.
Yes, Professor Baran, we are listening to your question.
It's very nice.
Yes, I'm listening. Thank you.
And now this everything done in case of topology spaces, right? That's I understand.
Yes. For Tikhonov spaces.
Yeah, can this happen? Can be done in case of convergence spaces, like filter convergence spaces, limit spaces, Kent spaces.
I didn't consider this, but probably it is possible.
And
here in this approach, the main thing is that we restricted already defined notion of probability measure on compact spaces to the Tikhonov space, thanks to Stonechair compactification. Maybe something similar can be done for convergent spaces. I don't know, but you can try.
I think can be done in case of
okay.
Yeah. Okay. Thank you.
Okay. Thank you.
Any question, either online or face to face? No question. More question. Thank you very much, Professor Kocinac.
Thank you for your attention.
Professor Kocinac, can I ask you other things about
Hi.
question?
Hi, Osman. How are you?
How are you?
I'm fine.
Oh,
I'm fine. You are also fine?
I am great. Okay, thanks.
Okay,
And
okay.
by the way,
Bye-bye.
are you joining the topology session today and tomorrow?
At some point, yes.
Yeah, we are pleased to see you there.
Okay, so see you.
Okay, see you
Bye
there.
bye.
Okay, thanks.
Bye.
Thank you. Thank you,
Bye.
Kocinac.
Thank you.
See you in. You can look at your email box.
Okay.
I sent a file.
Okay, thank you. Thank you. I'll check.
You are welcome.
Bye bye. Have a nice time.
Now it's lunchtime. We will go down to the ground floor. Then at the ground floor we will have lunch.
Hüseyin Hocam, katılımcılar için sınırsız yemek
Ha,
kartı.
farklı tamam.
Aynen, aynen. Güzel.